Hello everyone, and welcome to today's SAM webinar on modeling photovoltaic systems in SAM. My name is Paul Gilman. I'll be presenting today, and I have several of my colleagues on the SAM team who will be helping out with the question and answer. This is the second in our series of webinars for 2020. You can find registration information for upcoming webinars on the events page of the SAM webinar. And we'll also be posting links to recordings of those webinars on the events page. And you can find recordings of older webinars on the videos pages that are scattered around on the SAM website. If you have a question for today, please use the question box to type it. And either one of my colleagues will type an answer while I'm presenting, or they may interrupt me to ask the question so I can answer it, or we may hold it to the end for the Q&A session at the end. So I'm going to go through detailed design steps I'm using a residential PV system as an example, but the steps are the same regardless of whether you're modeling a residential rooftop or a farm system or a utility scale power generation system. I'll go through the steps for string sizing, and then I'll use a utility scale system as an example to show the tracking and self-shading options. And then I'll go over some of the shading, soiling, snow, and other losses and how they're handled in SAM. And then I'll briefly discuss P50, P90 simulations, importing data from other models, and then we'll have a Q&A session at the end. So first, a quick introduction to SAM. It's the System Advisor model. It's free software developed and distributed by NREL with funding from various sources, but mostly the Department of Energy. And it fundamentally does two things. It has a performance model that calculates a power system's energy output over 1 year by running hour by hour or up to 1 minute simulations, and a financial model that calculates a project's cash flow on an annual basis over a multi-year project period. The earlier webinar from this year, Introduction to SAM, is on the homepage of the SAM website. So if you'd like more about SAM's general capabilities, you can watch that video. So I'm going to start with a residential PV system, which is designed to reduce the electricity bill of a homeowner's home, and so it's typically installed on a residential property. We're going to focus on the performance side of things, so we won't talk too much about the financial aspects, but those are covered in another webinar, Electricity Rates and Bill Savings, which is available also on the SAM website. So I've chosen as an example this PV system in my neighborhood in Portland, Oregon. And it kind of has a unique design. It has two arrays, or the array is divided into two sections, one facing east and one facing west. So it's a useful example for showing various design options in SAM. So the first step is going to be to choose a performance and financial model. And then for each model, there's a number of sub-steps. So we're just focusing on the performance model, where we'll start by getting weather data, then we'll choose a module and inverter, and then design the system. So let's switch over to SAM and see what that will look like. When you start SAM, you're presented with this welcome page, which has some announcements from the SAM team. You can use these buttons down here at the bottom to get version information, for example, to open the help system. There's also some quick start options down here. But we're going to be starting a new project, so I'll click Start a New Project. And we're modeling a photovoltaic system, so I'll expand the photovoltaic list there. And I'm going to choose the detailed PV model. That's what we're focusing on here. But I'll briefly mention PV watts. So this is an implementation of NREL's online PV watts calculator. It has a simple representation of a PV system where you just provide it with a nameplate DC capacity, and it makes a bunch of assumptions about the modules and inverters in the system. It's implemented here in SAM, so you can couple it with SAM's financial models. The detailed PV model involves choosing a module and inverter, and then building the system by telling SAM how many modules and inverters are in your system. So it has a more accurate representation of the PV system. We're going to focus here on the residential owner model for this first example, and that's a distributed financial structure. So it's in the distributed list. So I'll click residential owner and click OK. And when I click OK, SAM creates a case, which is named untitled here. And I could rename that to something more useful. And you'll see that all of the inputs are populated with default values. So we're here on the location and resource page, and there's a weather file for Phoenix that's chosen by default. And you can flip through the other input pages to see there's a sun power module and this SMA inverter. These are just the default module and inverter for this sample system that is the default. And it's a 4.6 kilowatt DC system, and so on. So the reason we set things up this way is because there's lots of inputs in SAM, and this allows you to, right from the very beginning, run a simulation and look at the results to familiarize yourself with the model. So you can see that when you run a simulation, the results page appears with this summary tab, some high-level summary information about the results. And we'll be looking at all the different ways we can look at the results in our example. So this is the default system, but for my example here, we're going to be making some changes. So let's go to the next step, which is to download a weather file. So SAM has the capability of downloading weather data from NREL's National Solar Radiation Database, the NSRDB. And you can do this by providing a street address or a generic location name or a latitude longitude pair, basically anything that would work in a mapping application like Google Maps or something. It can download TMY data, single year data, or multiple files for P50, P90 analysis. The NSRDB is an online database that provides a weather data for the locations shown in this map at this point in time, but the database is being expanded, so we can expect it to cover more over the next few years. If you're interested in learning more about the NSRDB, we have a video on that on the SAM website here. And there's also the weather data page on the SAM website, which shows you other sources of data if you're wanting to model systems outside of these locations. So when you've downloaded your file in SAM, it goes out to the NSRDB, downloads the file, and then puts it into your solar resource library, which is shown in this list of files on the location and resource page. So let's switch over to SAM and see how that's going to work. I'm modeling this project in Portland, and I could type a street address for the specific house, but I'm just going to type Portland, Oregon, which will get me a location somewhere downtown, I imagine. Now click download, and it's determined that I already have the file. I downloaded it already, so it skipped the download, but it selects the Portland file in my solar resource library. Okay, so now that we've downloaded the weather file, we'll go to designing the system. So the system design has a few steps. We have to figure out what size the system is in kilowatts. We'll choose a module and inverter. and do our string sizing and array orientation inputs. So let's go ahead and see how that goes. So the first step is to define the system size, and SAM requires that you have a DC kilowatt capacity in mind when you're designing your system. It's not a sizing tool per se, and so you need to do some work outside of SAM to figure out how big your system is going to be. And this is a simple back of the envelope approach you could use to estimate the kilowatts for a given roof area or ground area. So I've determined that there's about 35 square meters available for solar modules on this roof, and that's about 5 kilowatts or 5,000 watts DC. Okay, and then I'm also going to just assume a 1.2 DC AC ratio to give me my inverter capacity. I could choose a different number, but for starters, I'll do that. So that results in a inverter capacity of about 4,200 AC watts. So 5,000 DC watts divided by 1.2. Okay, so let's go over to SAM and choose our, I guess I have some another slide to show you here. So we're going to choose our inverter next. We decided on a 4,200 watt inverter. So you go to the inverter page, and you can, where you'll find another library. This one is a library of inverters, and we can click column headings in the table here to sort the table by different parameters. In this case, we're going to sort by the AC power rating of the inverter. And then you click a row in the table to choose the inverter, and the parameters are populated down here. So in SAM, we'll go to the inverter page, sort by PACO, and find the 4,200 watt inverters, and there's a whole bunch of them there. And I've just arbitrarily chosen this PVI 4.2, let's see, 240 volt inverter. All right, next is the module. And I'm just gonna do an initial guess here. Since I have a 5 kilowatt array, if I choose 250 watt modules, that divides evenly into 5,000, giving me 20 modules. And I'll use that as my the starting point for my design. So I need 20 modules of 250 watts each. And I'll go to the module page, and and in this case, I'm gonna look through the Trina modules. I just chose Trina arbitrarily to show you how the filter feature works. So you type the name, string in here of Trina, and then this filters the list in the library to show only Trina modules, and then I can sort those by STC in this case, the rated module, the power rating for the module. So let's go ahead and do that. So I'll switch over to module, filter to Trina, sort by STC, and find the 250 watt modules. Which are down here. And I've arbitrarily chosen the 250 PA. These are all pretty similar for my purposes. It doesn't really matter which one I choose, but I'll pick that one. Now, if you're modeling a project and you have a particular module or inverter in mind, and you don't have, and it's not in the library, you can use this other option here, which is the model with user entered specifications. And here what you do is you provide data from a data sheet. So you need the manufacturer's data sheet, you get the parameters off of there, put them in here, and then SAM will calculate the coefficients that it needs to model the inverter. There's a similar, sorry, that was for the module, and there's a similar option for the inverter. It's called the inverter data sheet option. So there are options if you're modeling module or inverter that's not in the library. Okay, so now we've chosen our module. The next thing is to do some string sizing. To do that, we need two pieces of information. We need to know the inverter voltage limits and the module open circuit voltage. So the inverter here has an operating voltage range between 100 and 480 volts. And this module has an open circuit voltage of 37.6. So we can use that information to come up with a minimum and maximum number of modules per string. I made these calculations using a slightly different module, but the results will be close enough. So this tells us that we can use between 3 and 12 of these 250 watt modules and be within the inverter voltage ratings under design conditions. So that works out nicely. I have 20 modules, so I can just divide that evenly into 10 and I'll be within my voltage range. We can go to the system design page to do our string sizing. And as we saw before, we're designing two strings of modules that are facing east-west. So to do that, we're gonna set up two separate subarrays, and we're gonna connect each subarray to a separate MPPT input of the inverter so that they can operate at different voltages. So the first step is to enable subarray 2, and then modules per string is going to be 10 for each subarray. And then we have one string in each subarray. And this now we can check our subarray open circuit and maximum power voltages here. So that's just 10 times the module voltages. And then if I model it like this without doing anything further, this is going to connect both subarrays to the same input of the inverter. And Sam will just average the array voltage, the subarray voltages to calculate the inverter input voltage. Alternatively, there's this option down here to do PV subarray voltage mismatch, where you can have Sam calculate the voltages rather than just do that averaging. But we're gonna connect each subarray to a different input on the inverter. So we need to go back to the inverter page and tell Sam that we think this inverter has two MPPT inputs. There's no information in the library about the number of inputs that the inverter has, so you have to go to the inverter datasheet to confirm that this inverter actually has more than one input. And I did do that. This inverter has two inputs. So I'm going to set that number to 2 here. And then we go back to the system design page. And now we have a new input, which is the inverter MPPT input. So this is the input number. We have input number 1 and input number 2. And I can either assign the value by hand or I can click this button to do it automatically. Okay, so now we've done our string sizing and set the number of strings. And the next step is to set the array orientation. So we have 2 subarrays. The roof is a fairly shallow slope, so it's a 10-degree tilt, and each array faces east and west. So we do that down here under tracking and orientation. And we can use this diagram here to figure out what angles to use. So it's 270 degrees for the west-facing subarray and 90 degrees for the east-facing subarray. Okay, now we're done with our system design. So we're ready to run a simulation, and then we can refine our design. So let's go ahead and run the simulation. Click Simulate down here. And I've just ignored all the financial inputs because we're not focusing on that for now. And on the Summary tab, I can see that this system produces 4,800 kilowatt hours in 1 year. So that's for a 5 kilowatt system. It has a capacity factor of about 11.1, which is fairly low. And we have these other metrics, the energy yield, which is a measure of the annual output per unit of capacity, of array capacity, and the performance ratio, which is similar to energy yield. I won't go into detail describing these metrics here, but they're described in help. If you go to the performance metrics section here, we've got annual energy capacity factor, energy yield, and performance ratio are here described with their equations. The monthly energy production graph shows us a little bit more. This is showing the total electrical production by month. And we can see that we have pretty low output in the winter months and most of our output's in the summer. And we'd expect that from a fairly northerly location in the Pacific Northwest, where it's cloudy and rainy most of the winter. And then the fact that the array is facing east and west kind of exaggerates that effect. Those initial sort of high-level metrics give us a sense that it looks like the system is being modeled as we expect. We can dig in a little deeper by going to the Losses tab. And this is a Sankey diagram that shows the initial energy available to the solar array. So this is the solar energy incident on the array, plane of array irradiance, all the way down to the electrical production of the system. And you can see all these little arrows showing where either there's losses in the system due to soiling or shading, or there's conversion losses due to just the operation of the equipment. So if all these little arrows are relatively small, then we can assume that things are looking fine. But if you see a very wide decrease in energy at any point, that may be an indication that there's something wrong with your design. And then we can also dig into the hour-by-hour operation. This is we're using hourly weather data, so we're getting hourly outputs. This time series graph will show 5-minute data, 1-minute data, 30-minute data, depending on your simulation time step. So we can see this is the hour-by-hour generation. This is the first year. We can zoom into a particular day. We could also plot the voltages if we want to see what's happening on the subarray level. So there's all kinds of data to explore here. You can also explore this time series data on these other tabs. So the Profiles tab are daily averages by month. That can be useful for troubleshooting or analyzing your results. The Statistics tab is handy. It shows you minimum average values of all the hourly or sub-hourly inputs. So you don't have to calculate those outside of the model. And then the heat map here is also kind of handy. It gives you a snapshot of the entire year in one graph. So it goes from midnight to midnight. The middle of the graph here is noon. And then it goes from January to December along the x-axis. And we're showing the electrical power generated by the system, and the dark blue here is -2. That's because the inverter is consuming power at night. And our peak production is 3.8, which happens here in July during the clear summer days in Portland. And so you can see that in the winter, the sun is rising later, setting earlier. The summer, it rises earlier, sets later. So this is a useful snapshot of the entire year. Okay, next I want to show you how to use the system sizing macro to find alternate designs of your system. Maybe I'll pause for a minute to see if there's any relevant questions for now.
I think we're good, Paul.
Great, thank you. So the SAM has a built-in scripting language, which we call LK. This is sort of analogous to VBA in Excel. It allows you to write your own little programs within the SAM user interface. So you can manipulate the value of inputs. You can read the value of outputs, run simulations. You can read and write data to files, and so on. Now we have a set of pre-written scripts that we call macros to perform various supporting functions. And so this one is called system sizing, and it generates a report of design and operating voltages based on the simulation results and a set of design constraints that you specify. It also generates a list of modules that will work given your system design. So if you want to try a different module, you can use that macro to see which ones would work. So what I'm going to do is take our design, which is here, and I'm going to see what happens if we change the number of modules per string. Because maybe if I use fewer modules, I could reduce the cost of the system by reducing hardware costs or labor costs. There may be various reasons why I might want to use fewer larger modules. So first what I'll do is show you the macro with our existing system. So the macros are down here under the simulate button. You click macros, that gives you a list of the macros that are available for the residential PV models. The one we're interested in is system sizing. So I'll click that. It has some instructions that you can read. It has some input parameters for the macro, which I'll just leave at their default values. These are design constraints that come out of this approach, sort of a conventional design approach that's documented in this kind of old Solar Pro magazine article at this point. Anyway, let's just run the macro to see what it does. So you click run macro, and it's doing some stuff. It gives you some feedback down here. And when it finishes, it shows me this report. And at the top of the report is a table showing the input parameters that come from the input pages. And then it shows power losses from inverter, either power limiting or voltage clipping. There are none of those in this design because we designed it pretty conservatively. And then it also shows these graphs, which there's one for each subarray. And the orange lines here are the inverter voltage limits. So VDC on the x-axis, there's our 100-volt minimum and our 480-volt maximum. And then these bars are various voltages. The operating voltages, so this is the maximum operating voltage of the array over the year, and this is the minimum voltage. So we want to make sure that both of these are in between these two lines as far as the inverter is concerned. But if we want to do a more conservative design using these design constraints, or the worst case scenario, our minimum worst case design VDC is here just below 250 volts, and our maximum worst case design VOC is just above 400 watts. So we'd want to make sure that our operating voltages stay within that range. So this gives you a quick visual check that your voltages are within your design requirements. It also gives you this table of DC to AC ratio given different light-induced degradation scenarios. So SAM doesn't explicitly model light-induced degradation, which is the degradation that happens when the module first goes into operation, when it's first exposed to light. there's an initial degradation, and then there's a longer term degradation that happens over multiple years as the module cover degrades, and that's accounted for by this degradation input here on the lifetime and degradation page. So we assume there's a 0.5% per year degradation in the array's output and its DC output from year to year. That's accounted for, and you could change this value to a different number. But this is showing what your DC AC ratio would be given different LID scenarios. So we assumed a nominal DC to AC ratio of 1.2 or 1.19. This is what it would be if the LID degradation was 1.5 and so on. And then here is the list of modules from the library that will meet your design criteria here. And you can see there's a bunch of Trina 250 watt ones. I think it lists the first 50 modules listed in order of decreasing VOC. And then down here is a list of modules from other manufacturers that would also work with your system design. Okay, so that was for our 10-string system. If I go back to the system design and change the number of modules per string to 7 and run the macro again to see what modules it suggests I use. So it takes a minute. It's running through a simulation. And this one, I get a simulation message which tells me that the inverter is oversized. So the inverter only ever operated at about 60% of its rated capacity. That's because my array is smaller now. I reduced the array size, but I didn't reduce the inverter size. So that's expected. I can ignore this error or this message and can continue. And what I'm interested here is just to see what other modules it suggests. So if I stick with Trina, it's saying that these 335 watt modules would be good if for my 7 module strings. So then I can go back here and change the pick one of those 335 watt modules. And proceed with my design. So then I can run a simulation here. So now I have a system that has only 7 modules, and it produces about the same amount of power, slightly less than the 10 modules per string system did. So I guess my point here is just to point out that these macros are available, and also that when you're running SAM, you usually use it iteratively. So you do an initial design, and then you look at your results and think about them, and then change some inputs and do some more runs to see if you can improve your design. Okay, next I want to show a couple of examples using a large-scale system, just so you'll believe that SAM can do more than a small residential system. So there's no limit to the size of the system SAM can simulate, and the design process is the same whether you're designing one of these giant systems. You could use the subarrays to represent different blocks within the large system, and all the other parameters are basically the same. So this would be for a large PPA project. So instead of using the power to reduce a homeowner's electricity bill, you're using the power to generate revenue for a company. I'm going to use this example to illustrate the ground coverage ratio and self-shading. So we'll go back to SAM, and I'm going to create a new file now. So if I want to save this one, I'll save it as my residential example. And these files are saved as .sam files. So anyone else who has SAM can open a .sam file that you send them. and then I'll create a new project. And this one is going to be a PPA project using the single owner model. And we'll see here we have another default case. This one's also in Phoenix, Arizona. It uses a different module and inverter than our residential default system did. And it's for a 20 megawatt project. If we run a simulation, we see it produces about 37 million kilowatt hours, has a capacity factor of 21%, so a lot better than our residential system did. We're going to focus here on the tracking options. So the first thing we'll note is that this default system has a fixed array tilted at 30 degrees. So again, rename this fixed 30. And now I'm going to make a copy of this case by duplicating the case. And I'm going to make this one a one-axis tracking case. So I'll change the name of the case, and then I'll change tracking here to one axis. So if I have two identical cases, the only difference is that the I changed fixed to one axis tracking. That gives me this notice saying non-zero tilt was assigned for single axis tracking system. So what this is saying is that Sam noticed that my tilt angle is 30 degrees and he thinks that's pretty unusual for a one axis tracking array. This is a notice, so you can just ignore the notice and continue on and with your results. But I actually agree with Sam in this case, so I'm going to go back to the system design page and change my tilt angle to 0, because that's really what I meant to do. And I click simulate. Now the message doesn't appear. And I can compare the annual energy for the one axis tracker to fixed tracking just by clicking through these tabs. So our fixed at 30 degree tilt has a capacity factor of about 21.2% compared to 26%. So just changing the axis tracking option improved our performance. Now I also would need to change the costs here if I was doing a financial analysis, because the tracking, one axis tracking is going to be more expensive to install than the fixed array. So I'd need to probably increase my BOS cost assumption here. But I'm ignoring financial stuff for now. Now, next, let's look at what happens if we change the ground coverage ratio. So the ground coverage ratio is a way to indicate how close together parallel rows of modules are. The lower the GCR, the farther apart the modules are. And I'm going to do this GCR comparison with fixed arrays. So I'm going to delete my one axis tracking case here. So, not duplicated, delete. They both start with D. All right, so let me duplicate this fixed and I'm going to change this GCR to an extreme 0.9, so the rows are very close together. And this one, the GCR is 0.3. Okay. Now, so I want these two cases to be identical except for the GCR. So I could do that by just going over to the system design page here and changing the values. But I'm going to show you this inputs browser, which is handy when you're working with multiple cases. It shows you a list of all of the variables in the case. Right now it's set to show variables that are different between the two cases, and it's telling me that the inputs are identical. But you can choose show all values here to show a list of all of the variables that are in your case. And you can actually export this list if you want to, if you need the list to document your work. So if I change this GCR value to 0.9 and then go to my inputs browser, I can see that the only difference between these two cases is the GCR value. All right, so let's run a simulation between these two guys. So GCR 0.9 has a capacity factor of 21.2. That seems like it's the same as the capacity factor for my 0.3. So the GCR is not affecting the output. Why is that? Well, the reason is because I didn't tell SAM to account for self-shading. So by default, SAM is not accounting for self-shading or shading between rows of modules. In order to do that, you need to enable self-shading. And there are two options for self-shading. There's nonlinear, which is for standard crystalline silicon modules, and there's thin film or linear. So the nonlinear option assumes that your modules have 3 bypass diodes, and so a third of the module is taken out at a time as a shadow passes over the module. Whereas the thin film module assumes that the array responds linearly with the percentage of the array that's shaded. So these modules are monocrystalline, and so I'm going to use the standard nonlinear option. Now, when I chose the self-shading option, I got some red text down here, which is saying that the number of rows in subarray 1 is not an integer. It says I have 671.75 rows. Well, that doesn't make any sense. That's because I haven't told SAM what the physical layout of the array is like. So on the system design page here, this is the electrical layout. We have 12 modules per string and 5,374 strings in parallel. But for the physical layout, we need to have numbers that are consistent with those system design, the numbers on the system design page. So I'm going to say, just to keep things simple, that the way this array is laid out, the electrical strings are, each physical row has 2 electrical strings on it, and the modules are in portrait position. So basically the rows look kind of like this. There's two rows of 12 modules in each physical row. That gives my number of rows integer value, and the message goes away. Now I want my my 0.9 GCR scenario to have the same values, so I'll use the inputs browser to set the inputs here to make sure that they're same. So I want the GCR to be different, but I want to use this for the number of modules per row, and then for my shading option. Okay, and then now I can run a simulation and run another simulation for the other case. And so now we see the results with self-shading accounted for, and we can see that the extreme scenario with the rows very close together has a much lower capacity factor than the other case did. Now I can take this a step further and use a parametric analysis to run through a range of GCR values. So let me set that up for you. So I just click parametrics here, and then I'm going to use the quick setup tool to choose the ground coverage ratio for subarray 1. We just have one subarray in this system. And then, so now that variable is added, and then I'll click edit here and define the range of values. So I want 0.3 to 0.9 in increments of 0.1. I'll update. So this is going to consider these GCR values. And then for my outputs, I'm going to show annual energy, maybe capacity factor. And I'm going to add a cost metric here, because the whole point of using GCR in your analysis is to spacing. You're looking for the optimal spacing where you want to maximize the output of the array, but you also want to minimize the cost of the array. So as you space the rows further apart, you need more land, and that's going to cost more. So in order to account for that, we do need to make sure that we're accounting for the cost of land. So I'll just sneak in here to the system cost page, even though I haven't described it to you yet, and jump down to the land purchase cost. And I'm going to change the land cost to $3,000 an acre. So this way, as the array size changes due to the GCR, the land purchase cost will change. And that I'll go back here to Parametrics and run simulations. And now we have a set of results for each GCR. We can see what the capacity factor is, so it's going down. And then the net present value, we can see that it's going down as you increase the GCR. So you're using less land, but you're also generating less electricity. So the net present value doesn't go down as dramatically as the annual output does. Okay, I want to leave some time for questions, so I'll just quickly go through the next items. I didn't spend much time talking about external shading and snow loss. That's because those are covered in a separate video, which is shown here on the PV videos page of the SAM website. But particularly for residential systems, but any type of system, you can import external shading data from shading analysis software or shading analysis tool. SAM has a built-in 3D shade calculator that will generate shading data for you based on a picture that you draw of the array and nearby shading objects. And when snow data is available in your weather file, you can use a snow model to estimate the effect of snow loss. And this paper here describes that feature. And this reference is also included in the publications page for the PV model on the SAM website. SAM also has a P50, P90 analysis feature, which basically runs a simulation over a set of weather files for a given location. So it runs a simulation for each year in a historical period and reports that these statistical numbers called P50, P90. I've outlined the steps here. You can, on the location and resource page, you choose this download files for all years option, and then click download, and SAM automatically downloads all the files you need for a P50, P90 analysis and puts them in a folder. And then it actually displays instructions for you to what to do next, which is to come over here to the P50, P90 page, navigate to that folder that contains all those files, and then just click run. And then you get these metrics here. Again, we have a video describing this on the weather data videos page of the SAM website. You can import data from other models into SAM. We have a macro that imports weather files and also the files that contain inverter and module parameters from PVsyst. So if you're doing comparisons between SAM and PVsyst, you can do that fairly easily. And then the solar resource file converter macro can import weather data from a few different sources, including the European Commission's PVGIS and Solar Anywhere, which is a commercial product. I believe some of the other commercial products like Meteonorm provide weather data in SAM format already, so you don't need to convert it. And PVGIS actually provides the weather files in the EPW format that, that SAM can also read without converting. And then if you're using a different model to model the PV system, and you'd like to use that data with one of SAM's financial models, you can use the generic system model to import the generation profile. You could also use that if you had measured data from a plant and you wanted to run a financial model with real measured data. So a few options for importing data from outside of SAM. And that's all I had prepared. This slide collection will be posted with the webinar recording, and it comes with some extra information that I didn't cover here, but it shows some different examples of string layouts and how to set them up in SAM. And it also provides a little bit more information about the financial models. So that'll be available for your reference with the webinar recording. So I will stop talking now and open the floor for questions.
Great, thank you, Paul. We do have some questions that would be great to cover with the whole audience. One of them was about system losses. If you could go through a little bit what types of losses are calculated versus input and how they're reported.
Yes, yeah, thank you for that. That's an important question that I sort of glossed over. So there's a whole page here, input page dedicated to losses. And you can see that the losses are divided into different categories. We have irradiance losses. So these are losses that are applied to the plane of array irradiance before it goes into the module model. And then we have DC losses. So these are losses that apply to the output of the array. And then AC losses apply to the output of the inverter, and then some additional losses. Soiling losses here are pretty important, and the default value is 5%. So that's something that is kind of hidden in the inputs, is that we're automatically taking 5% off the available solar radiation on a monthly basis to account for soiling. So obviously you can change these values. You know, you could use lower soiling values for a rainy season and higher soiling values for a dry season, for example. Then on the DC side, we have this set of losses that is used to calculate the total DC power loss. You know, generally you can just use these default values unless you have a reason to change them. And then we do have these buttons to help you assign DC loss values. So if you're modeling microinverters, for example, you don't want a module mismatch loss. So if you click microinverters, that sets that to 0 for you. And if you're running DC optimizers, then there's some losses associated with the power electronics. So we add a DC power optimizer loss. If you're running central or string inverters, then you can use these default losses. And then we also have these, what we call system availability losses, which are customizable. So you can assign losses on an hour-by-hour basis, or you can have losses that apply during certain periods. So you could use this to model system shutdown for maintenance or a number of other applications. And those are available both on the DC and AC side of the system.
Great, thank you, Paul. There was also a question on the sort of more broad side of system sizing. If you have a particular goal in megawatt hours of energy that you're trying to produce in a year, perhaps you could demonstrate how to use parametrics to get your system to the right size for that. type of generation goal?
Right. So I showed you how to size the array, specifying modules per string and strings in parallel. I didn't show you that there's this calculator here. So if your system has a single subarray and you want to just get some quick results and not worry about the layout, you can use this option, and SAM will do its best to figure out the number of strings and the number of modules per string to meet your requirement. So this works particularly well for large systems where the size of the modules compared to the array is small, so you can easily figure out, adjust the number of modules to get close to your target size. So in this case, there's a target desired array size of 20 kilowatts, and the actual size here is that it's 20 megawatts, sorry, 20,000 kilowatts. And then our desired DC-AC ratio is 1.2. So if we put the system design page into that mode, then we could go to the parametrics, and we'll replace the parametrics with, let's remove that variable, and we'll add desired system size. And then we could I'll just put a range, and let's say 5,000 or 2,500. I don't want it to take too long. So we'll try a few different sizes here. And then we'll set the outputs. We want annual energy. Get rid of these guys. Let's see, where's that variable? It's system output. Okay, now if we run, and I also want to show the actual system size for the, let's see. Size. There should be a well, can't find that on the fly here, so I'll skip that step for the moment just to show you how this works. So we'll run simulations, and we have shading enabled here, so we're getting some of those messages. But just to give you the concept, we have for each size here, we have the annual energy. So if you had some target you were trying to meet, you could figure out, if you were trying to get to this annual capacity or annual generation, then you'd know that would be you need a 15 megawatt system.
Great, thank you, Paul. I know we only have a couple minutes left. There were maybe 2 more questions that I think would be broadly relevant, so maybe we'll go a minute over. One is, can I look at the PV system models used by SAM? I think this means the underlying code.
Great, so I'll take this opportunity to show you around some of the other resources for SAM. So there's the SAM website, which hopefully you're all familiar with. This is where you download SAM, and you can find links to all the videos, recordings of these webinars that we make, and so on. Another resource is the GitHub repository. So this is where the source code, SAM source code, lives. So you can read about the various code bases that are available that SAM is built on here. And the performance models, or the underlying models, are in this other repository called SSC. And you would find the source code for the photovoltaic model in CMOD PV-SAM v1. So we're just looking at this C++ file in a web browser. You can't really navigate through the code very easily. But if you're interested in we'll get through all these input variables, interested in how the models are implemented, you can explore these repositories on GitHub. And we have a forum dedicated to the open source project. So if you have questions about the source code, you need help finding something, or a question about how to build the model if you're trying to build it, you can use this forum. And then of course we have the general forum and a forum for the software development kit, so that if you have questions for us, please get in touch with us on the forum. This is moderated daily, so you should get a fairly quick response if you post a question here.
Great, thank you, Paul. And the last question that we'll cover live for today was just touching on bifacial systems. I wonder if you could quickly show people where they should go to model bifacial panels.
Yeah, so I think I mentioned, provided a link to a video that'll be in the presentation slides, so you can find that to get some more detail. But I'll show you the bifacial input is fairly straightforward. It's on the module page, and you just check this box and you provide these inputs. So the module library actually does indicate whether the module is listed as a bifacial module or not. So if this bifacial parameter is 1, then it's a bifacial module. And if you choose one of those and don't enable bifacial, then you get this little message. I don't know, I'm not 100% sure that all the modules that are indicated as not being bifacials are not bifacial. So it's a good idea to check your data sheet and before you model a module as being bifacial. It's also handy if you want to just do a theoretical comparison and say, well, what if my one-sided module was bifacial? What would it do to my project economics? So yeah, once you choose enable the bifacial model, then you need to provide a transmission fraction, bifaciality factor, and this ground clearance height. And those parameters are described in help. I think we even have a handy diagram, yeah, to help you figure out how to calculate the transmission fraction.
Great, thank you, Paul. I think that's it for live questions for today.
Cool, thank you. And we will, for the questions that were answered in the chat window, we'll make a transcript of those that'll be posted in a PDF along with the video, so you'll be able to refer to those after we post the video recording. So thank you all very much for your participation in today's webinar. We hope to see you at one of our upcoming ones, or hear from you on the support forum or by email. Hope you have a great rest of your day, and we'll hear from you soon. Goodbye.